All right, so let's look at a proof of Euclid's proposition number 36. So what we have in this case is that we have a couple of parallelograms, and the bases of those parallelograms are going to be congruent, and the sides opposite those bases are along the same parallel lines. Now, what the proposition says is that the area of those two parallelograms are going to be equal. So let's see if we can prove that this is going to be the case. So kind of using proposition 35, if we draw a couple of lines, so if we draw the line between BE and our point CH, then if we knew that the quadrilateral BCHE was going to be a parallelogram, then proposition 35 tells us that the area of parallelogram ADCB is going to be equal to the area of parallelogram BCHE, but then also the area of BCHE is going to be equal to the area of FGHE. And so in that case, what we would have was that the two areas of our parallelograms, ABCD, was equal to the area of EHGF. And that's what we wanted to prove. The only drawback is that we don't know for sure and for certain as it is that BCHE is going to be a parallelogram. And so that's what we need to prove. All right, so if we kind of look at these bases that we have here, so now let me turn that parallelogram off and that parallelogram. No, maybe I want that one. Then if we look, because we know that segment BC is going to be congruent to segment FG, we can kind of do the same trick that we did before and add on the segment CF to each one of those. And so our segment BC plus CF is going to be congruent to our segment CF plus FG. And that's going to be by common notion 2. And so what that gives us is that our segment BF is going to be congruent to our segment CG. All right, so now for the angle here, because we have CE parallel to GH, we know that our angle FGH is going to be congruent to our angle BFE because they are corresponding angles. So we know that those two angles are going to be congruent. And then also by our proposition 34, we know that the length of the segment FE is going to be congruent to the length of the segment GH because those are opposite sides of a parallelogram. And so what we've actually constructed is a couple of triangles, and for those triangles, so we've constructed this triangle BFE and the triangle CGH. Now we know that the bases are going to be congruent. We've said that the angle here, BFE, is going to be congruent to our angle CGH. So those are going to be congruent, and the sides FE are congruent to side GH. And so that means that our triangles BFE is going to be congruent to our triangle CGH by our side angle side congruence property. So what we then have is that our angle here, our angle BEF, is going to be congruent to our angle CHG. So we've got this angle congruent to this angle. Now, if we kind of bring back our parallelogram again, we also know that our angle FEH is going to be congruent to our angle GHI because they are corresponding angles. And so what that means is that by our common notion 2, this angle plus this angle then is going to be congruent to this angle plus this angle. So our angle BEF plus our angle FEH is going to be congruent to our angle CHG plus our angle GHI. And so what that means is that our angle BEH is going to be congruent to our angle CHI. Now, what that gives us is that we have corresponding angles that are going to be congruent, and so our corresponding angle congruence theorem then says that our lines BE has to be parallel to our line CH. And so what that means is that our parallelogram, so our quadrilateral BCHE, is actually, sure enough, going to be a parallelogram. And since it is a parallelogram, Proposition 35 then gives us that our two original parallelograms, ABCD, is going to be the area of that is going to be congruent, is going to be equal to our area EFGH.